This is section 5.3 on definite integrals and antiderivatives. In table 5.3 we have the rules for definite integrals. The first one is the order of integration. If you integrate from b to a, that would be the opposite of integrating from a to b. You give the opposite sign. So what this is saying is if we have a function and we're integrating from a to b, integral from a to b, if the area is above the x-axis, then this answer would be positive. But if you integrate backwards, if you integrate from b to a, then this answer is now going to be negative. In the second one, the integral from a to a of f of x is 0. Well, imagine having a rectangle from a to b. So if you integrate to a to b, there's a rectangle. But if you integrate from a to a, there's no rectangle, it's just a line. There's no area with a line. So if you integrate from 5 to 5, there's no area there. The answer is just 0. Constant multiple, if you have the integral from, let's say, 0 to 3 of 4 times f of x dx, you can write that as 4 times the integral from 0 to 3 of f of x dx. So you can pull the constant out, and then you don't have to worry about it for evaluating the integral. Same thing with a negative. If this is a negative 4 in here, you could pull the negative 4 out, and that's what they're saying here. You can pull the negative 1 out. Sum and difference. If you add two functions and take the integral of the addition of those two, you can split them up individually and get the same answer. Same thing with subtraction. In the additivity, if you have, let's say, a function from a to b and then b to c, if you want to find the area from a to c, you could integrate just from a to c, or if you had to, if there was a reason to, you could integrate from a to b, and then integrate from b to c, and that would be just like integrating directly from a to c. That's the additivity rule. In domination, it says if f of x is greater than g of x, so in other words, you have two functions. Here is g of x, and f of x is above g of x. Here's f of x. So it says f of x is greater than g of x on a to b. So from a to b. What this is saying is the area under f of x is going to be more than the area under g of x. Well, there's more area up to f of x than there is up to g of x, and hopefully now that I've described it a little bit, that is somewhat intuitive. If f of x is greater than 0 for the whole interval, so if the function is above the x-axis from a to b, then they're saying that the area will be positive. So you calculate this area, the function is above the x-axis the entire time, so the area must be positive. Using the rules for definite integrals, we notice we have negative 1 to 1 of f of x is 5, 1 to 4 of f of x is negative 2, and negative 1 to 1 of h of x is 7. So if they want to know what is the integral from 4 to 1 of f of x, well, if 1 to 4 was negative 2, then this answer is going to be the opposite of that. It's going to be positive 2. In letter B, if we're integrating from negative 1 to 4, that's like integrating from negative 1 to 1, which is 5, plus integrate from 1 to 4, which is negative 2. So this answer is 3. That's the additivity one. And you have additivity as long as those two are the same value. In letter C, we're integrating from negative 1 to 1. For f of x is 5, so we have 2 times 5, plus 3 times negative 1 to 1. For h of x is 7, so we have 10 plus 21, looks like 31. In letter D, we are evaluating the integral from 0 to 1 of f of x, and from negative 1 to 1 is 5, and it is not half of that. We do not know if this graph is symmetric from negative 1 to 1, so not enough information. Letter E, from negative 2 to 2 of h of x, well, we don't know if this is symmetric, and we can't just double these and double this. You can't do that. So this one is not enough information either. We don't have enough information to evaluate this. In letter F, we have negative 1 to 4 of f of x. Well, we could find out what negative 1 to 4 is. We actually did that over here. So this is actually 3, but we have no information for -1 to 4 for h of x. So this one we can't do either, not enough information for the last 3. For the average value of a function, it says if f is integrable from a to b, its average value on a to b is 1 over b minus a times the integral from a to b of f of x dx. Now, the reason we have this is, well, we can find the average of, let's say, 3 test scores. Someone scores a 40 out of, let's say, 50, someone scores a 30, and someone scores a 20. That would be 60, oh, that's kind of worked out nice. 90 divided by 3, the average would actually be a 30. But those are kind of separate values, and if someone scored a 30 and someone scored a 40, there's no guarantee that someone scored a 35. Well, if we wanted, let's say, the average temperature for the day, if the temperature goes from 10 degrees to 50 degrees, the temperature was all of the degrees in between at least a brief moment in time. So, how do you find the average of a continuous function versus the average of just some individual values? Well, you have to use calculus. You have an infinite amount of values from 10 to 50, and that's kind of what this is doing. It's summing up an infinite amount of rectangles under the function. So we need to know the function to find the average value. And then when we divide by 3 here, that's like dividing by b minus a. So if we're going from let's say 2 o'clock to 5 o'clock, we end up dividing by 3. That's very similar to average over here. So here's adding everybody up and dividing by really how many there are. It's kind of that way. In example 3, we want to apply the definition, and we want to find the average value of f of x equals 4 minus x squared on 0 to 3. Does f actually take on this value at some point in the given interval? So we want to, well, let's look at what the graph looks like. It has a y-intercept of 4. It has a 0 at 2 and -2, but we're only worried about 2. And then we're going all the way to 3. So if we plug 3 in, we get 4 minus 9, which is -5. 2, 3, 4, 5. So the parabola looks something like that. And we want to know the average value from 0 to 3, but we have an infinite amount of values, so it's not like we have some to add up and then divide by how many we have. We have to use calculus. So we have 1 over 3 minus 0. That's 1 over the b minus the a. Times the integral from 0 to 3 of 4 minus x squared dx. We're going to use our calculator to find this answer. So we have, we use FNINT, we put the function, the variable from 0 to 3, and we get 3 for the integral part. So we have 1/3 of this ended up being a value of 3, and 1/3 of 3 is 1. Now we want to know, did the function ever take on this value? So if the first answer is 1, that's the average value. Does f actually take on the value at some point in the given interval? Well, let's find out. We got 1 equals 4 minus x squared. We have -3 equals -x squared. So x squared equals 3. So x equals the square root of 3. So yes, when x is the square root of 3, the function has a value of 1. So 4 minus the square root of 3 squared, that's 4 minus 3, there's the 1. The mean value theorem for definite integrals, if f is continuous on a to b, then at some point c in a to b, the function value will equal the average value, and that's exactly what we just showed. Find an integral using antiderivatives. Find the integral from 0 to pi of sine of x dx using the formula. So to evaluate from a to x, you take the antiderivative of the function, plug in x, minus a plugged into the antiderivative. So if lowercase is the function, uppercase is the antiderivative. So when we do this one, we have to go backwards now. We're not taking the derivative of sine, we're taking the antiderivative of sine. So we have to think of, what did we take the derivative of to get sine? Well, the derivative of cosine is negative sine. So if I make this negative, the derivative of this would be negative sine, which is sine. And then we're going to evaluate this from 0 to pi. So that is the antiderivative right there, negative cosine of x. So to evaluate this, we plug in the top value. You plug in x first. So we have negative cosine of pi minus negative cosine of the lower value, 0, which is equal to, let's see, cosine of pi is negative 1, so negative negative 1, and the cosine of 0 is 1, so minus negative 1, because just the cosine is 1 right there. So we have 1 plus 1, the actual value is 2. We want to evaluate the integral using antiderivatives, just like we just did in example 4. So we have to think about what did we take the derivative of to get secant squared, and that's the tangent. And we're going to evaluate tangent from 0 to pi over 4, which is the tangent of pi over 4 minus the tangent of 0. And the tangent of pi over 4 is square root of 2 over 2 over square root of 2 over 2, which is 1. And then the tangent of 0, here's 0 right here, 1, 0, sine over cosine, 0 over 1, that's 0. So the answer is 1. On 24, we got to think about what did we take the derivative of to get 3x squared. Well, when we take the derivative, we minus 1 from the power, so now we're going to add 1 to the power. And if I take the derivative of this, it ends up being 3x squared. So you take the derivative of x to the third to get 3x squared. We're going to evaluate that from negative 1 to 2, which is 8 minus negative 1. 2 to the third is 8. Negative 1 to the third is negative 1. So the value is actually 9.